All right, welcome. Today is Monday, February the 8th. We spent the first part of the day today kind of going over and finishing up calculations on the lab. The lab is going to be due on Thursday. You'll turn in the hard copy on Thursday when everybody's here. Virtual kids, you just go ahead and submit it online. All right? Now, we were looking at these practice problems, number 29. It's pretty obvious. It's just times 2 and times 2. So we get x and y equal to 1. And so how do we calculate k? So the rate law, so the answer to A, rate is equal to k times CO times NO2. So how do we get k? Just plug in the values, okay? So I always pick the first one, the rate, 3.4 times 10, what, 10 to the what? I can't read it. Negative 8 is equal to K times CO, 5.1, 10 to the minus 4th, times 0.35, times 10 to the minus 4th. So what does K equal? 1.9
molar over.
Okay, so this is molarity per second, or molarity per hour. Okay, molarity, so we're gonna always be per molarity times hour. You always have to be able to do the units on this. All right, so now number 30 is gonna be very similar. Okay, so if I'm looking at number 30, let me move it up.
Oh wait,
Okay.
when it asks for 0 first, second order, do you do it like?
Well, you say it's first order with respect to COs, first order with respect to NO2, second order overall.
Second order overall. Okay, so you add them.
You add the exponents for overall order.
Okay.
Okay, so number 30. Same thing. This is times 2, so we know that this is going to equal a 1. Then keep these two constant, so we go here, this is times 3. So we look at these two, and what's that going to be times?
9.
Times 9, right? Now, that you may not be intuitively obvious as far as what that is, so go ahead and always divide the big one, divide by the small one. So it's really, notice it's 10 to the minus 2, 10 to the minus 1. This is 1.2 going into 11. Okay? But it's going to be times 9. So what does that make the exponent on B? 2. Okay, now you do the exact same thing here, except we're going to end up getting, 9 is equal to 3 to the y. Okay, because we changed the concentration times 3, but the rate changed by 9. So we can see that y equals 2. And then you do everything else the same. So what is the rate law? Rate is equal to K times A times B squared. Okay? What is the overall order then going to be? Third order. And could this reaction occur in a single step? Probably not, because 3 things having to combine together, all in the proper orientation, is very rare and very hard. Okay? And so it's probably going to be a multi-step, and we'll talk about how to do that. That's the last thing we have to talk about. Hopefully we'll get to some of it today. And how can the bell hit ring? Oh, they're doing ACC to ACT testing. Okay? Makeup or something, I don't know. So if you guys need to take a break, or we're just ready to keep just going on?
I gotta turn this in real quick and then we can go.
Took the ACT on Saturday for the first time.
Really?
Yeah.
Sorry.
And
You'll see in 2 weeks, huh?
The English section was the worst. The science was the easiest for me.
Oh, good. $1981's the next one.
Alright, Mr. Hobbs, just gonna say this is late, but
That's fine. I won't look at it. We did 81 in class, didn't we?
yeah.
Okay, so I don't have to go over that one. And then, what was the next one?
89.
All right, I think you're ready to roll. We'll just get done with this. All right. Account for the following observations regarding the exothermic reaction represented by the equation above. An increase in the pressure of the reactant causes an increase in the rate of the reaction. Okay, Ben, what did you put for that?
I said that increasing the pressure increases the number of collisions between the molecules, which in turn also increases the probability of the proper orientation where reactant bonds begin to break and product bonds begin to form.
Perfect answer. You gotta have all that. Increased pressure, increases collisions, increases probability of proper orientation, where reactant bonds begin to break and product bonds begin to form. Okay? I know it's long, but that's complete. Perfect answer. A small increase in temperature causes a large increase in reaction rate. Anna, what'd you get?
I said the increase in temperature allows more molecules to overcome EA, so the reaction speeds up.
Perfect. Okay? Okay, Nishka, why does a metallic nickel cause an increase in the reaction rate?
Nickel's a catalyst, so it lowers the activation energy that's needed. So mostly the molecules then have the needed energy for the reaction.
Okay, so more molecules have enough energy to overcome EA. Okay, so nickel's a catalyst, it lowers EA, so more molecules have enough energy to overcome EA, so the reaction proceeds at a faster rate. And then lastly, what is powdered nickel? Why is it, what's gonna be different? More surface area, which allows for more collisions at any given point, which increases the probability of proper orientation, dot, dot, dot. Okay? So these are good things, just be able to get theory questions, a possible short answer question, possible multiple choice questions, kind of along those lines. You good with that? What's the next one?
92.
93.
2.
92?
Mm-hmm.
All right, H2 plus I2 makes 2HI. For the exothermic reaction carried out at 298, the rate law is as follows. Predict the effect of adding each of the following changes on the initial rate of the reaction. Explain your prediction. So if I had hydrogen gas, increase in the concentration does what to the rate? Lauren, what you get?
I said increased concentration of hydrogen gas will increase the number of collisions through molecules, which increases probability of proper orientation where reactive bonds break.
Okay, perfect. It's almost the exact same answer, you know, as Ben, and both were perfect, okay? Increases collisions, which increases the probability of proper orientation where reactant bonds begin to break and product bonds begin to form. Okay, now, what will an increase in the volume of the container What net effect is that gonna have? Initially.
It will decrease, because an increase in volume is equal to decrease in concentration.
There you go, good. So did you hear what she said in the back? An increase in volume is, what was your exact
So
word?
an increase in volume is equal to a decrease in concentration.
Is equal to a decrease in concentration, which then is gonna be the exact opposite answer one that Lauren just gave, which decreases the number of collisions, which decreases the probability of proper orientation. That's good. I just wanted, the main thing on this one, I just wanna make sure you understand, increase in volume of gases is like decreasing concentration. Okay? So good. So addition of a catalyst, include a diagram of potential energy versus reaction coordinate. Okay, does everybody understand what that graph is? That's your potential energy graph. Okay, and this is potential energy. This is reaction coordinate. Progress, whatever you want to say it. And it says exothermic, right? Yes. So what does that mean? Where does product need to go?
Below.
Needs to go below, right? So what does the catalyst do?
Decreases activation.
Does it change the energy of the reactants? Does it change the energy of products? So it's just going to be with the catalyst. Yeah, that's all showing up on it. Okay. All right. And then increase in temperature. What does an increase in temperature do, Anna?
It increases the energy that the molecules have to overcome EA, so the
Okay.
reaction would proceed faster.
So the reaction proceeds faster. Now, if I said to explain that in terms of a temperature distribution graph, okay, what would we draw? I mean,
Max.
The Maxwell bulletin.
right, okay. So this time I would draw this graph, and at T1, it's gonna look like this, and here's EA. And if I increase the temperature to some new temperature T2, what's gonna happen? It's gonna flatten out, right, and spread out, because the range, the same area under the curve, just a bigger range. But now notice we have a lot more area under the curve, meaning the number of molecules, and this is energy. It's really kinetic energy, or the speed of the molecules. A lot more area under the curve, therefore many more molecules with enough energy to overcome EA. Okay, so you need to be able to know these two graphs very well. We all good with that? We've done it enough. Hopefully it's, implanted in your brain. You won't even have to study. All right, what's the next one?
2000A.
2008?
A, like.
2000A, this one.
Yeah.
Enthalpy, that was last unit. I thought it would be a good flashback to just kind of show how they kind of intertwine concepts together. So referring to the data, calculate the standard enthalpy change for delta H. Okay, so I have delta H of formation, so what equation do I want to use to solve this? Say it loud enough for me to hear.
The H of the products minus the H of the.
Okay, the heat of formation of products minus the heat of formation of reactants. Okay, so I'm looking at my equation. What's the heat of formation of oxygen? What's the heat of formation of any element always? 0. That's why it's not in the table. Plus NO2, 33. minus O3, 143, plus the NO is 90. So it's going to be 233 and 33, what's it gonna come out to? Negative 200. And that's gonna be kilojoules right there. All right, so then B says, make qualitative prediction about the magnitude of the standard entropy change for this reaction. What can we say about the magnitude of entropy given this? First off, what's the word magnitude mean?
How big?
How big it is. Just how big it is. We have sign and we have magnitude. We have, is it positive or negative, and then how, is it a big or a small number? Magnitude always talks about how big or small the number is. Okay, so whenever you're reading that, that's what, make sure you interpret that. What do we know? How do we remember, how do we determine delta S from an equation?
Moles of gas.
Moles of gas. What's the difference in moles of gas here?
0.
0. So what do we expect about the magnitude of delta S?
Small.
It's going to be very small, near 0. Okay? So entropy change isn't going to have much of an effect on this one because the moles of gas equal each other. So then the final question is, on the basis of your answers, part A and B, predict the sign of the standard free energy change delta G. Well, delta G is equal to what? What's the equation?
Delta H minus T delta S.
Minus T delta S. So if this is very small here, okay, very small delta S, pretty much all going to be based upon delta H, right? Which we know to be negative. Since delta S is very small, have very little impact, therefore delta G will be dependent mainly on delta H, which is negative, so delta G will be negative. All right, so that's just all flashback. So now we're in a thermo question, so my brain is thinking thermo, 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 and then all of a sudden now D. I see this. Well, I gotta change gears now because it's no longer a thermo question, now it's become a kinetics question. So you gotta realize that these AP questions aren't thermo questions, they're not kinetics questions, they're not stoichiometry questions, they're chemistry questions that are gonna intertwine all those concepts together, so you can't have tunnel vision. So now, we gotta work on E. We don't know how to do E yet, so hopefully you didn't struggle too much. Did I say A through D? Did I specify anything on this one? Okay. I don't know how I missed that. Okay. So, here, this is constant, this is times 2, this is times 2, therefore, this is a 1. We can keep these two, we can compare this. This is times 2, this is times 2, therefore, that's a 1. Okay? Write the rate law for the expression. So what's the rate law going to be? Rate equals
K.
times O3. And what's the name of O3?
Trioxide.
No. It's a pollution in the lower atmosphere and we need it in the upper atmosphere. Ozone. Okay, so we can, it'd be good if we just, well, I don't want to keep that on here. We just remember that that's ozone. And then times NO to the first. Now, we'll come back to that. This is the last thing we need to talk about, how to do this. So we'll just skip over that. I should have somehow said, don't have to worry about that one. Y'all probably just looked it up on the internet, put an answer down. What was the next one?
2010.
Here's another one. That's 2009. All right, chlorine can be generated in the lab by reacting potassium permanganate, that's pretty potently poisonous, purple potassium permanganate, which we're gonna use later on this year, with an acidified solution of sodium chloride. Where in this equation does it say, how do I know there's an acid in here? When it says an acidified solution. What part of that equation tells me there's an acid? All acids contain which ion? H plus, right? This right here is my acidified chloride solution. Now, they probably may just put HCl in there, but notice it's a 4 here, so they put more acid other than just HCl. It doesn't matter what the acid is, the anion will be a spectator. We just have a bunch of H plus. Okay, that's just, I mean, that's kind of foreshadowing of what's coming at the end of the semester. All right. So the net ion equation given above, a 25 ml sample of 0.25 molar NaCl reacts completely with excess. The chlorine produced, dried, and stored and sealed at 22 degrees. The pressure of the chlorine is 0.95. So I have chlorine gas. I have a temperature. I have a pressure. What has to be coming to your brain?
PV equals nRT.
PV equals nRT, okay? Now, I have 25 milliliters, okay? NaCl, this is going to be a spectator, so this is going to be 25 milliliters of 0.25 molar, okay? Calculate the number of chloride ions present. How do I figure out the moles of chloride ion present? I have a volume and a molarity. You multiply. Molarity times volume equals moles. So again, we have a stoichiometry problem here. So we're just going to say 0.02500 liters times 0.25 moles per liter. That comes out to 0.001. How many zeros? All right, I mean, pardon me, it's going to be time, so it's going to be 625.
Yeah, 00625.
0.065, let's divide them initially. And that's going to be moles. Okay? Now, again, you have to recognize that in a net ionic equation, you're only putting the parts that react. You're getting rid of your spectators. So a 25 ml sample of NaCl reacts with the KMnO4. So here's my MnO4. Here's my Cl minus. This is the acidified part. Okay? So you just don't worry about the spectators. You gotta say, well, NaCl is not anywhere in the reaction. But it is. Because we're just doing a net ionic equation. So now calculate the volume. Well, volume is equal to nRT over P. Well, I know the temperature. I know the pressure. I always know R. What don't I know? I heard mumble. N, which is, what does N stand for? Moles. So I need moles of chlorine. So N equals moles of chlorine. So I need to know that. Well, what did I just calculate? Moles of Cl minus, right? But if it goes to completion, 4 makes how much chlorine? 2. So how many moles of chlorine am I going to have? This divided by 2, right? So it's going to equal 0.00625 moles times 2 moles of chlorine for every 4 moles Cl minus 0.003125. Okay, so now I have everything I need to just plug in here. So volume is equal to 0.003125 and 0.0821. Temperature is 22. We got to change that to Kelvin. So it's 295 divided by nRT over V, over P, 0.95 atmospheres. And what do we get? 0.0797. We have 4, we have 3, let's go to 0.0797, and that's gonna be liters. Okay, now, were you guys able to figure that out without looking it up? No?
All but the last
All of the down here, this
one.
other?
Or, no, the one that you just
Oh, with this one?
Yeah.
Okay. So again, this is where when I see the gas, I know I'm gonna have to do this. So I write my equation. Then I'm saying nRT over P. Well, what do I already know? Well, I know RT and P, that's just given. So what else do I need to know? If I'm gonna be able to find volume, I have to be able to know all of these. So how can I find moles of chlorine? Well, I come back to my equation, I'm looking for X moles of chlorine. Well, what did I just find? Well, I know how many moles of Cl minus I have. So then you just do the stoichiometry to get to the moles of chlorine. Okay? So always just say, okay, well, I know I'm gonna use P equals nRT. What do I know? What do I still need to know, and how do I get to it? All right? That's a good problem solving technique. And I included these just because I thought it was a good flashback, you know, to remember how to do some of these problems. So now here we go, we switch from a stoichiometry gas law problem to a kinetics problem. So now we have to figure out what Cl minus and MnO4 are. So this 0.01, what's that going to be times?
3.
Times 3. What's this times? Okay, so I'm going to have to say the change in rate from experiment 1 to 2 is equal to the change in the concentration of Cl minus to the X. So 9 is equal to 3 to the X. X equals 2. So that's what you kind of put right here. I should have put that right there. Okay? So then the MnO4. Well, these two are kept constant. Let's go this way. So that's times 2. That's times 2. So what do I know what MnO4 exponent is?
1.
A 1. But you still say change in rate, and I would say 3 to 2 is equal to the change in the MnO4 minus to the y. 2 is equal to 2 to the y. Y equals 1. But what does the question ask? Okay, determine the order. You haven't proven yet that you know what the order is. Okay? You and I both know that X and Y are the order, but you have to specify it. So you would say, so it is first order with respect, or let's just even say for first order for MnO4. So it is second order for Cl minus. Okay, so you have that over right here for this, and then you just state that what the order is. Okay? Got to answer the question. I know that's picky, but you can't assume that they know what you know inside your head. They don't have you all day, every day, you know, for 180 days. The reaction is known to be third order with respect to H+. Okay? Third order here. Wow. Write the rate law. So rate, I'm going to go over here for C. What's rate going to equal?
Cl minus
Cl minus times MnO4, the permanganate ion, to the first, times H plus to the third. So what's my overall order? 6. 2 plus 1 plus 3. Okay? Calculate the volume of the rate constant in appropriate units. Now, you guys went through and did that. We just plug in. What did K turn out to equal, the number?
I got 0.00193.
Okay, so now think about units. It's molarity per second. So if this is molarity per second, we have molarity squared, molarity cubed. This is going to be molarity to the 6, but one of them is going to cancel out. So it's going to be per what? Molarity to the 5th times seconds. It's always whatever it is total over here minus 1 on the bottom. And then the last question is it logical? Do you think this can occur in one step? No, there's no way that 6 molecules can all collide at the same time in the proper orientation. The probability is just way too low. Okay? Really, it's only 2 molecules hitting is the greatest probability. Anything over a second order reaction is probably not feasible. Are we good with all this so far? Yes? Everybody's good. All right. We only have a couple more, don't we?
That was it.
That was it? Oh, that's even better. All right. Big breaths. Now we're going to change gears again. So we know how to do rate laws. We know how to do the differential rate law. We know how to do the integrated rate law. There weren't any integrated rate laws that were assigned there. We did a bunch in class, though, of practice AP problems we just have already done. So you need to be able to do that. So you always calculate K. You can calculate the rate law using both forms of the equation. Now we have this thing called the reaction mechanism. Reaction mechanism. It's a series of elementary steps that describe how a reaction may proceed. Okay, so now I have to define, what do I mean by elementary steps? An elementary step is a simplified reaction that occurs, that always occurs, in one step. If I just look at all the reactions that we've been looking at so far, we can't just look and say, assume it's an elementary step, that it's just going to be A plus B makes C, that those two are going to collide. We usually think there's going to be a series of steps that it's going to follow. Well, in that series of steps, each step is called an elementary step, and that is what you assume definitely occurs in one step. Okay? But you have to pretty much be told that it's an elementary step. every step of a mechanism is going to be an elementary step, okay? Now, WYSIWYG. Back in the day, well, I've already kind of confessed how old I am today. Okay, we were talking about that, the fact, you know, that I took chemistry in 1976. When I started teaching in 1982, okay, there weren't laptop computers. I did not have a computer in my class. But somewhere around I think is when I went to Baton Rouge High in 1987, is that I had my first computer in the classroom, and it was an Apple IIe computer, very primitive, basic computer with the green screen, and it was very basic. And when you went to print, we had the dot matrix. It was like a typewriter, and it had the little circles on the end that the gears would go through, and you may have seen it on old movies where it prints it out super slow, loud, whatever. But I'm getting to a point. What you would see on your screen and what would come out on the printer weren't always the same thing. So you'd always have to adjust where your margins were, where you indented to, and all of that kind of stuff, because it just kind of all got messed up on the formatting going from the computer to the printer. But somewhere in the late 80s, early 90s, they came out with WYSIWYG. Is that, and I think it was all with Windows, but what you see on the screen is what prints out on the printer. And that was huge. Okay, so we all call it WYSIWYG. What you see is what you get. That's what happens with an elementary step. What you see is what's happening. There's no other intermediate steps. There's nothing else that's forming. It's just what you see is what you get. WYSIWYG. Okay? So, in our reaction mechanisms, you're going to have this series of elementary steps that are all happening in individual. Now, there's always going to be a slow step. The slowest step is called the rate determining step. Okay? In elementary steps, the coefficients are the exponents in the rate law. Okay? In elementary steps, we get to use the coefficients because it's WYSIWYG. What you see is what you get. So we know how many molecules are having to collide in this slow step. Okay? And I always like this to where, you know, at your family, you know, let's just say it's time to go out to dinner, you're going to go to church, you're going to go somewhere together as a family. Everybody gets ready, but there's always that one person that you're waiting on. Okay? One person that, I forgot this, or, you know, they're putting their makeup on, or they just can't find a shoe, or, you know, it tends to be that one person that always, you know, slows you down. That's the rate determining step. You would have been on time to dinner, beating the rush, if it wasn't for the person taking 15, 20 minutes longer than everybody else. The rate determining step. You've maybe heard a chain is only as strong as its weakest link. A relay team is only as fast as its slowest member. Okay? You could have 3 Usain Bolts on a 4x400 or whatever, and if I'm number 4, we're losing. Okay? Because everybody's going to pass me because I'm going to be the rate determining step. That's why I wore that T-shirt the other day that said if I ever had to run for my life, I would probably die. You know, it's just, okay, it's just I'm slow. So, the coefficients can be your exponents, but we always just look at the rate determining step, the slowest step. Alright? And a lot of times it's going to be slow, or we can figure it out from the rate law. Because there are two criteria for a mechanism to be valid. Two criteria. Now notice that I underlined over here, may proceed. Nobody knows for sure how the reaction proceeds. We can't see the individual things that get formed. Okay? But for it to be valid, for it to even be a potential of possibility, you have to meet these two criteria. Number one, the steps of the mechanism must add up to the overall equation. This is kind of like a Hess's law thing. The individual steps have to be the same. Once you add up the steps of a mechanism, they have to be described the overall equation. So we just add them together, cancel out things that are the same, and that needs to come out. So we call this the stoichiometry criteria. Okay? But the second one is the rate law of, can I call this RDS, rate determining step, so I don't have to write that out every time. The rate law of the RDS must be the same as the rate law, as the experimentally determined rate law. And the experimentally determined rate law is what we just did when we determined what X and Y are from the data and the tables and all that stuff. Okay? And in our rate determining step, we get to use the coefficients as our exponents. Okay? Now, I needed to find two more things, and then but I'm going to do that kind of as we're in the middle. So let's go back to that one I said, ooh, you probably don't know how to do. Is that 1994?
It was 2008.
2008. There we go. Do that one. Let's look at this mechanism. Okay, so what did we determine the rate law from this experimental data? What did we determine the rate law to be? From our previous problem. I think we found that it was 1 and 1, right? So we said the experimentally determined rate law was rate is equal to K times O3 times NO. And they are both to the first power. So now, when I'm looking, each one of these is what we call the elementary step. So I need to find out which one of these is going to have the same exact rate law as this one. Well, so if I look at this, what's the rate law of this going to be? Well, it's going to be rate is equal to K times O3 times NO. That's exactly the same right there. Okay? What's the rate law of this one going to be? What would we say the rate law of this one would be?
K of O.
K times O times O2. But we use coefficients as, oh, well, pardon me, I looked at the wrong thing, O3. Okay? But that is not the same as this one, so this can't be the slow step. The reality is this is the answer, because it came out exact. But here, I just want to see, okay, rate is equal to K times NO3 times NO. Which again, is not the same as my experimentally determined rate law. Therefore, this must be the slow step. Because the rate law, the rate determining step equals the overall rate law. Okay? Now, we could go through and look at this, okay? So in this case, notice that O is being produced here and then consumed there. O is not a reactant or a product. It's going to be called an intermediate. Okay? So an intermediate is neither a reactant nor a product. It is, I'll put a comma, I think I need a probably semicolon. It is formed and consumed in the reaction. Okay? So it's not the beginning or the end, it's something that's formed in the middle. It's an intermediate. Intermediates are not included in the reaction mechanism. Pardon me, the rate law. Intermediates are not included in the rate law. So what's another intermediate that's here? NO3. So this is an intermediate, and the O's are intermediates. Okay? Now notice that if we add all these things up, we're going to get it's going to be a 2 O3s, 2 NOs makes 2 NO2s, but then we just, eliminate the 2's to get the overall equation. So it adds up, stoichiometry, and then the rate law, the rate determining step equals the overall rate law. So this is called a reaction mechanism. Let's look at another one. I don't know if I want to do all of this. Let's find one in the book. This is on page 625. Okay? So here we have chlorine plus ozone, you have ClO plus O2, ClO plus O goes to Cl plus O2. Okay? So first off, what's the overall equation for this?
O3 plus O is 2O2.
Okay? So notice the CL's are going to cancel out. So the O's are going to cancel out. No, it doesn't. Does it? Nope. Because we have O2 over there.
No, it's O3 plus O goes to 2O2.
O3, oh yeah, the CLO's cancel out right there. O3 plus O goes to 2 O2s. All right, now, notice the chlorine. Is that an intermediate? Is it formed in the middle of the reaction? Now, this is something we added at the beginning, but it ended up getting regenerated at the end, right? This is a catalyst. So a catalyst in the mechanism is the thing that gets formed, you put it in there, but it gets reformed, so it doesn't get consumed in the reaction. It changes in the middle, but it's the same at the end as it was at the beginning. So where's my intermediate in this? This is my intermediate. Okay, so in the mechanism, we need to be able to identify the difference between a catalyst and an intermediate. You don't always have a catalyst. Okay, but a catalyst is included in the rate law, just so you know.
Will there always be intermediates?
Almost always, yes. I haven't looked at this one, we'll just see. Now notice here, they're telling us that this is the slow one, right? Just seeing what you're so enthralled with over there, there's something going on.
Sorry, I was looking at your, progress card.
That's all right. All right, so notice they say this is the slow step, okay? What is the overall reaction? We can just add those up. We don't need to do that. What is the molecularity of each of the elementary steps? Now, the molecularity means how many molecules are colliding at any given point, okay? Here, it's chlorine just breaking down. So there's only one molecule involved. So the molecularity is unimolecular. Whereas here, there are two molecules involved. Bimolecular. Two molecules involved, bimolecular. Okay? If three molecules are somehow, it'd be trimolecular. Okay? So the molecularity is really just how many molecules are involved. So we say, what is the rate determining step? Well, we know this one is the rate determining step because it tells us it's a slow step. And then lastly, what is the rate law predicted by the mechanism? Okay? So the rate law of the rate determining step has to be the same as the experimentally determined rate law. So we just write here, rate is equal to K times Cl gas times CH3 Cl3. Okay? Now, tomorrow in class, this really, what's the problem with this? What is Cl in this reaction? It's an intermediate, okay? Because it's going to cancel. Cl is going to cancel here and here. And we don't put intermediates in the reaction rate law. So tomorrow, this right here, notice we have an equilibrium. We have a fast equilibrium. Tomorrow we have to go over, well, there's a proof where we have to do a substitution in here. Okay? But because what is the definition of equilibrium?
Equal.
What's equal? In equilibrium, what's equal?
Oh, the forward rate and the reverse
The
rate.
forward rate and the reverse rate are equal. So we're going to use that fact and be able to do a substitution in here to where we can eliminate this out of the rate law. Okay, but we don't have time today to go over that. Okay? So what you need to take away from today, know what a reaction mechanism is. I understand elementary step is WYSIWYG. What you see is what you get. Know in an elementary step you get to use the coefficients as exponents. Now, you cannot just look at an overall reaction and say it's an elementary step. You have to be told. It has to be given here. Okay? We need to know the two criteria that we have to have. They have to add up, and the rate law, the rate determining step equals that plus then you need to be able to identify catalyst and an intermediate. Okay? Tomorrow, let's just talk, tomorrow we'll be kind of going over that. That's the final thing we have to do. I feel good about overall problems. Wednesday might be Princeton review day for you at home. Thursday will be just a final review day and a test on Friday. I think we'll be ready for the test on Friday. Okay? Unless you have a bazillion other tests on Friday. Because technically, Friday is gonna be an even day, and I'm not supposed to give a test on an even day. But if you don't have a math test or anything else on that Friday, then we'll do it. If not, we'll have to wait until Monday. Do what? You do? What math is that? What level?
Advanced pre-cal.
Advanced pre-cal has a test?